common logarithms and natural logarithms. A common logarithm is simply a logarithm with a base of 10. This is an important logarithm because the number system that we use is actually base 10. So because this logarithm is so important, when we have a log base 10, we simply write log without writing the base. So anytime you see a logarithm without a base, that simply means that the base is 10. So for example, common logarithms of powers of 10 are simple to evaluate. So take, for example, log of 1,000. Well, we know that 1,000 is 10 to the third power. So log of 10 to the third power, the 3 can be brought down, and then we have 3 log of 10. But log of 10 is 1, right? Because, again, log of 10, there's an invisible base 10 right here, and all we're saying is, what is the power of 10 to get 10? Well, that's 1. So we have 3 times 1, which is 3. Now, of course, we could skip all that, and we can simply recognize that since 1,000 is 10 to the third power, the power of 10 to get 1,000 is 3. And we could do the same thing for all of these. So log of 100 is 2 because 10 squared is 100. Log of 10 is 1 because 10 to the 1 is 10. Log of 1 is 0 because 10 to the 0 is 1, etc. Now, when you get into decimals, it's a little bit trickier. So, for example, if you think of log of 0.01, remember that 0.01 is the same as 1/100th. And this has to be -2 because we know that 10 to the -2 power is equal to 1 over 100. Now, if for some reason you are given a logarithm of a number that is not a power of 10, then we simply use a calculator and we find the log key on that calculator. So for example, use a calculator to find the log of 2,760. Now, on most calculators these days, you are simply going to hit the log key, and then on your calculator, you will usually see something displayed like this, or sometimes they put a parentheses for you. And then you simply hit the numbers 2, 7, 6, and 0. Get in the habit of closing the parentheses, and then simply hit equals or enter, and your calculator will display the answer. And you can see here that we get the number 3.4409, etc. And it is customary to round this answer to 4 decimal places. So we'll say 3.4409. And of course, this is an approximate answer. Okay. Now, what does that mean when you do that? Well, it means if you take the number 10 and you raise it to the power 3.4409, you will get approximately the number 2,760. Now, I should note that on some calculators, the process is reversed. So on some calculators, you actually hit the number first, and then you hit the log button. But on most calculators that are made now, you will type it in like so. So a couple of other examples for you, and if you have a calculator handy, maybe you could just pause the video and check to make sure that you know how to enter this on your calculator. But the log of 0.0391 you should find to be negative 1.4078, and the log of 0.00523 is approximately negative 2.2815. So maybe just pause the video and double check that you can get these solutions on your calculator. Now, in the next example, we're switching things around a little bit. We have the log of x is equal to 3.8774. And we want to know what's x, right? So we're solving for x there. Now, keep in mind, the base here is 10, but this is not something that you simply plug in using your log key on your calculator. So we need to go back to what is the definition of a logarithm? Well, we know that this means that 10 raised to this power is equal to that number. So that is 10 to the 3.8774 is equal to x. And so now to finish this, we just need to take the number 10 and raise it to that power. And you can see that the number that I get for x is this number here. And so we're going to say that x is approximately 7,540.4975. Now, you could round to a different number of decimal places here. I'm just rounding to 4 decimal places, but make sure you pay attention to what you're being asked to round to. So once again here, we have log of x is equal to some number. So let's go ahead and write that down. This is, remember, log base 10 of x is equal to negative 2.4179. We'll keep in mind the definition of a logarithm, which tells us that this means that 10 raised to the power negative 2.4179 is equal to x. And now we'll just plug that into a calculator. And this gives us x is approximately equal to 0.0038. Logarithms are also used to measure the power of earthquakes. So the San Francisco earthquake of 1906 is estimated to have measured 8.3 on the Richter scale. So that means it has a magnitude of 8.3. And the San Fernando earthquake of 1971 measured 6.6 on the Richter scale. Find T for each earthquake and then give some indication of how much stronger the 1906 earthquake was than the 1971 earthquake. So we can tell that the 1906 earthquake was stronger because it had a larger magnitude, 8.3 compared to 6.6. But what does that actually mean? How much stronger was it? So to do this, we use the following equation. And this equation says that the magnitude of an earthquake is equal to the logarithm of t, where t is the measure of how much larger or how many times larger it is compared to the smallest measurable shock wave. So in this particular example, we have 2 earthquakes. We have the 1906 earthquake, which has a magnitude m equals 8.3. Then we have the 1971 earthquake, which had a magnitude of 6.6. So if we plug these into the equation, m equals 8.3 says that 8.3 is equal to the log of t, which means that t is going to be 10 to the 8.3 power. The other one tells us that 6.6 is equal to the log of t, and so t is going to be equal to 10 to the 6.6 power. So to decide how much larger the 1906 earthquake was, I'm just going to take the quotient of these two numbers. So if we take the number 10 to the 8.3 power, and we divide it by the number 10 to the 6.6 power, this is equal to 10 to the 8.3 minus 6.6, which is 10 to the power 1.7. And now if I just plug that into a calculator, we get approximately 50.1. So this is a ratio of the powers of these earthquakes. That means that the 1906 earthquake was 50.1 times more powerful as the 1971 earthquake. Next, we define the natural logarithm. A natural logarithm is a logarithm with a base of e, where e is the special number approximately 2.72. Whenever we deal with a natural logarithm with this base e, we write the logarithm as the natural log, and we use the abbreviation ln to represent the natural log. Some examples here. We know that e to the 0 is 1 because any number raised to the 0 is 1. We know that e raised to the first power is equal to e. Therefore, the natural log of e would be 1, right? Because the natural log of e asks the question, what is the power of e to get e? And of course, that's the first power. What is the power of e to get 1? Well, that would be 0. What is the power of e to get e cubed? Well, it would be 3, wouldn't it? What is the power of e to get e to the negative 4? Of course, that would be negative 4. And what is the power of e to get e to the t? Well, that would be just t. So now let's use the properties of logarithms to expand the following expression. We have the natural log of a multiplied by e to the 5t. So because we have a product here, we can say this is equal to the natural log of a plus the natural log of e to the 5t. This allows us to bring the 5t down here as a power, and so this becomes the natural log of a plus 5t multiplied by the natural log of e. And we know the natural log of e is equal to 1. So this simply becomes the natural log of a plus 5 times t. And sometimes it's a little bit better to just turn this around and say that this is 5t plus the natural log of a. And the reason we do this is because sometimes when you have something after a logarithm like this, sometimes people will think that we're taking the log of both of these things. But it's actually just the log of a, natural log of a, and then plus 5t. So if we move the 5t to the front, we know for sure that it's 5t, and then we're only taking the natural log of a, right, and adding those two things together. And this is as far as we can take it in this particular problem. Another interesting thing about logarithms is that we can use information about some logarithms to find other logarithms. And this is actually how logarithms were computed in the past before we had calculators. So for example, let's suppose that you know the natural log of 2 is 0.6931 and the natural log of 3 is 1.0986. Using this information and this information alone, so in other words, no calculator, can you find the natural log of 6? Well, it turns out we can, because we know that 6 is 2 times 3. So the natural log of 6 is the natural log of 2 times 3. Using properties of logarithms, this is the natural log of 2 plus the natural log of 3. The natural log of 2 is 0.6931, and the natural log of 3 is 1.0986. So if I just take these two numbers now and add them together, we get 1.7917. So the natural log of 6 must be this number here. And again, we can figure this out without a calculator. Now for our next one here, we have the natural log of 0.5. So how could we figure out the natural log of 0.5? Well, it takes a little bit of creativity here. So 0.5, let's remember, is 1/2. And 1/2 we can actually write as 2 to the negative 1 power. Properties of logarithms tell us that we can bring the negative power down in front. So this is negative 1 times the natural log of 2. And this is negative 1 multiplied by, what is the natural log of 2? Well, it's 0.6931. So this is simply going to be negative 0.6931. And finally here, how about the natural log of 8? Well, again, let's re-express 8 as a power of 2 in this case, so 2 to the 3rd power. Just like before, we can take this power 3 and bring it down in front. This is a property of logarithms. And we have 3 times the natural log of 2. This is 3 times 0.6931. Right? And we can do this without a calculator. So 0.6931 multiplied by 3 is 2.0793. So this is just kind of a fun way to use logarithms to find other logarithms. And that concludes this video lesson.